This is an experiment on passive filters. A filter is a useful device in signal processing. It will allow certain frequencies to pass through and block other frequencies. There are three types of filters commonly referred to. The low pass filter, it allows all frequencies below a maximum value, F maximum, and cuts off frequencies above F maximum. The high pass filter, it cuts off all frequencies below a minimum frequency F minimum and allows all frequencies higher than F minimum to pass through. A band pass filter is one which allows signals between a range of frequencies F1 to F2 to pass through and blocks frequencies outside this range. The figures show the transmission coefficient as a function of frequency for low pass, high pass and band pass. The dashed lines are for the ideal filter where transmission is a constant unity up to F maximum and abruptly goes to zero for a low pass filter. Similarly, for a high pass filter, ideal filter, transmission is zero up to F minimum, abruptly jumps to 1 above F minimum. And in band pass, it is 1 between F1 and F2 and 0 beyond. But actual filters do not have such abrupt cutoff. In an actual filter, the transmission coefficient will decrease slowly up to F maximum and then fall below a certain value when the frequency is more than F maximum. This is the transmission coefficient for an actual high pass filter, and this is a transmission coefficient for an actual band pass filter. Filters can be of two types, passive or active. Passive filters are made of components like resistance, capacitance and inductance, which are passive components. Active filters will have these components, but in addition they will have operational amplifiers or transistors. Here we will deal with passive filters made of resistance and capacitance. So in a low pass filter, we have a resistance in series with a capacitance. The voltage is applied to the series combination and the output is taken across the capacitance. So the ratio V output by V input, called the transmission coefficient, is the impedance of the capacitance 1 by 2 pi Fc divided by total impedance, which is R square plus 1 by 2 pi Fc whole square power half. We can see that when the frequency is low, 1 by 2 pi Fc, very large compared to R. So the ratio will be close to 1. When the frequency is high, 1 by 2 pi Fc becomes small compared to R. So the ratio becomes close to 0. The frequency at which R is equal to 1 by 2 pi Fc is called the roll-off frequency of the low-pass filter. At the roll-off frequency, T will be 1 by root 2 or 0.707. The high-pass filter again is a combination of a capacitance and resistance in series, but now the output is taken across the resistance. So the transmission coefficient is resistance by total impedance, which is R by R square plus 1 by 2 pi Fc square power half. When the frequency is small, the denominator is very large, and therefore transmission is very small. When the frequency is large, 1 by 2 pi Fc is small compared to R, transmission approaches 1. The frequency at which R is 1 by 2 pi Fc is called the roll-on frequency of the high-pass filter. At this frequency, T is 0.707. A band-pass filter is obtained by putting a low-pass and high-pass filters in series. There is the input to the low-pass filter. The output of the low-pass filter across the capacitor CL becomes the input for the high-pass filter. The output is taken across the resistance of the high-pass filter. The transmission coefficient is V output here divided by V input here is a maximum at a frequency f, which is square root of f roll off into f roll on. The three filters are realized in this box. At the right is the low-pass filter, and between the red and the yellow is the resistance, a pot which is set to a value of around 150 ohms. Across green and yellow is the capacitance 0.22 microfarad. You apply the AC voltage between the red and the green and measure the output voltage between the yellow and the green. The right side is the high-pass filter. Between red and green is a capacitance of low value, and between yellow and green is a pot which is set to around 4 kilos. The capacitor has a value 0.33 microfarad. You apply the voltage between the red and the green and measure the voltage across the yellow and green. The two greens are connected. For the band-pass filter, you connect the input of the high-pass filter to the output of the low-pass filter. You apply the AC voltage here, measure the output AC voltage here. I will now connect the low-pass filter to a signal generator. I will measure the total voltage across this. The input voltage at 200 Hz is 1.005. The output voltage is 1.003. I now make it 2 kilohertz. The output voltage has come to 0.79, while the input voltage is 0.897. Note, The signal generator is always giving 1 volt RMS. When you measure 1 volt RMS at low frequencies, below kilohertz, your DMM gives the correct value. As the frequency increases, the DMM will show a lower value. This is the DMM measures the correct value, RMS value, only at low frequencies, not at high frequencies. But here we are taking ratios of two values, so this error does not matter. So as the frequency is increased, the ratio comes down, and you can find out what is the role of frequency when the transmission is 707. For the high pass filter, you connect the input to the red terminal here. These two are shorted, so the other end of the signal generator need not be changed. Now we measure the input voltage, that is 0.953, and the output voltage, which is 0.638. If I reduce the frequency, output voltage is small, so it doesn't allow low frequencies to pass through, but it allows high frequency to go through. You will see the input and output ratio is nearly 1. So this is a high pass filter. For the band pass filter, I connect the input to the high pass, I connect to the output of the low pass. I connect the signal generator to the low pass filter. I measure the input between the red and green on the low pass side, and the output between the yellow and green on the high pass side. So you do it as a function of frequencies. There is a low pass filter, there is a frequency in kilohertz, 0.2 kilohertz to 10 kilohertz. There is a logarithm of the frequency, there is the input voltage, and this is the output voltage, and this is the transmission coefficient. So you plot transmission coefficient as a function of the logarithm of the frequency, you get a curve like this. You can measure what is the frequency at 0.707, and that is 4.92 kilohertz. You can calculate that frequency because CL is 0.22 microfarad, RL is 150 ohms. There is the data for high pass filter. Columns have the same significance, and this is the curve of transmission versus frequency. Transmission is low at low frequency and becomes 1 at high frequency. The roll-on frequency can be measured at 0.707 for the transmission coefficient, that is 0.966 kilohertz. Capacitance is not 33, resistance is 5000 ohms. And this is the data for the band pass, and there is a curve. So the maximum occurs at 2.42 kilohertz, which is square root of 0.966 multiplied by 4.92. Passive filters are very simple filters. Actually, one uses more complicated active filters.